Hi everyone, and welcome to Microsoft Research Forum. I'm Yash Lara, Senior Technical PM in the Microsoft Research AI Frontiers Lab, based in Silicon Valley. AI Frontiers is a mission-driven lab within Microsoft Research, founded in 2023. Our portfolio spans foundation and small language models, synthetic data pipelines, memory, agentic frameworks, and the systems and applications that bring them to life. Our work has been shipped through open source releases like the Phi family of models, Farah, Autogen, and the Magentic family. Our mission is to create the foundations of agent-native organizations through reliable models and agentic systems that learn, act, and collaborate alongside people safely and effectively. We're working towards that future by building deep partnerships both across Microsoft and throughout the broader research community, and contributing open source artifacts. While this collaborative approach is the hallmark of Microsoft Research as a whole, the AI Frontiers Lab is uniquely focused on translating cutting-edge advances into forward-looking, integrated agentic systems. Our research focuses on building foundations for the entire agentic stack, from architectures to models to harnesses and experiences. Today's episode is especially exciting as we highlight this work in action through a new, exciting release. We're also sharing new tools, methods, and ideas from across Microsoft Research Labs. You'll hear from teams working on agentic systems, developer tooling, model training, and the broader impacts of AI on how we coordinate and organize work. Across all of it, there's a common thread: how we build AI systems that are not just more capable, but more reliable, more efficient, and ultimately more aligned with people. Let's get started with a special announcement and release from our AI Frontiers Lab. Today, I'm excited to announce a new release from the Microsoft Research AI Frontiers Lab, MagenticLite. MagenticLite is the next generation of Magentic UI. It works across both the browser and your local file system in a single workflow, keeping you in the driver's seat at every step. Along with MagenticLite, we're also releasing the two models powering it. MagenticLite is a result of deep collaboration across AI Frontiers, spanning model development, agentic systems, agentic harnesses, and UX. Together, the team has created an end-to-end innovation throughout the agentic stack. We'll now hear from our amazing colleagues, Waili, Harkarat, and Hussain, who will walk you through MagenticLite and the models and demo it live.
Hi, I'm Waili.
I'm Hussain. And I'm Harkirat. And we are all members of AI Frontiers, a boutique lab inside Microsoft Research.
And for the past few months, we've been working closely together to reimagine what an agentic application can look like, one that's efficient, capable, and useful for getting work done.
To do that, we had to work on the full stack, rethinking everything from how we generate training data, how we design the models, how the harness orchestrates it all, and to the user experience that makes the whole thing feel like genuine collaboration.
What really moved the needle was going beyond standard benchmarks. We started with hero use cases, real everyday tasks that people care about. We built our own evals around them, and we used this signal to drive a flywheel of iterative improvements across the whole stack.
And the result today is 3 joint releases. First is MagenticLite, our experience where you can get a real feel of these small language models to get real work done. Second is our computer use agent model, Fara1.5 a state-of-the-art model for models at its own size class. And last but not least, Agentic Orchestrator, a model capable of reasoning, delegation, coding that brings the whole experience all together. And now Waili is going to show us how MagenticLite works.
Let's dive into MagenticLite. You may have heard of Magentic UI, the agentic application we released last year that set the foundation for this work. With MagenticLite, we have reworked the agent harness to run efficiently on small language models, making it faster, more lightweight, and no longer reliant on frontier-scale models. We also refreshed the UX design based on community feedback, making it easier and more natural to work with. MagenticLite works across both the browser and your local file system to help you get real work done, whether that's filling out online forms, making appointments on your behalf, managing files on your desktop, or generating simple code. Let's see it in action. I can give MagenticLite access to a folder on my computer. Here, I'm giving the notes from the last Microsoft Build conference. I want the agent to search for what has changed and create an update doc to help me prepare for the next conference. It has successfully accessed my notes and created to-dos. Next, it opened a web browser and started to gather the information I need. MagenticLite has access to its own browser running in a virtual machine. This helps minimize the risk of data leakage while allowing Farah, our browser use model, to operate fast in the browser. Farah performs well at long-running tasks. It looks like Farah has gathered enough info and the orchestrator has created a document. Let's check it out. MagenticLite did the job. It included updates on all key sections. Next, I'd like to email this document to my colleague. I'll let MagenticLite do this for me. I can keep working on other things, and MagenticLite will notify me when my attention is needed. In this case, it needs my help to log into my email account. I'm taking control of the browser to log in. Once unblocked, the agent is composing the email and can send it off once it finishes. Now that you've seen it in action, let's take a closer look at the models powering MagenticLite, small models that punch above their weight. Next, Harkirat will introduce Magentic Orchestrator. Off to you, Harkirat.
Thanks, Willie. So if MagenticLite is the app that you interact with and Farah drives the browser, then Magentic Orchestrator is the brain that ties it all together. It is the planner, the coder, and the delegator all in one model. Its job is to take a messy request, like the one shown here, book me a dentist appointment Tuesday afternoon and add it to my calendar, and convert it into a concrete plan. So the orchestrator figures out the steps, picks the right tool or subagent for each step, writes code when code is the right answer, and recovers when something breaks mid-task. What's interesting is that the recipe is very simple. Orchestration is usually where people reach out for the biggest model that they can get. The reasoning is hard, the failure modes are expensive, but we wanted to show you that you can push all of this down into a small model without giving up on capability. The training itself is plain SFT. We don't use any fancy multi-stage pipeline. But the main unlock here is the data mix. We blend two different and complementary styles of data in the right ratio. Next, I'm going to talk about these types of data. The first style is standard tool calling. Clear, simple function tool calling. A request comes in, you pick the right tool, you call it with the right arguments, and you handle the response. For this, we built an in-house pipeline, which we call Vulkan, that generates this kind of data. The trick, which is shown on the left, is that every tool is a Python object, with its own arguments and return types right there in the class. On the right, those tools become nodes in a graph, and a single trajectory is an ordered path through that graph. As you can see, it starts with a search, then it goes to book, then it goes to your calendar, then it goes to your email. So the model here lands a realistic multi-turn composition, not just an isolated tool call. We then validate each path with rules and a sandbox, and mix it with other data that we created, including MCP trajectories, which are both public and our own synthetic trajectories. This is done to broaden the tool coverage. The second style of data is terminal data. What you are looking here at the top is an actual cowork style trajectory. A user requests optimize all blog images to WebP. Then step by step, the agent takes an action in the terminal. For example, the action shown here is ls. The agent reads the results and decides what to do next. 10 steps like this for a single task. On the bottom, we show how we generate these trajectories at scale. A 4-stage pipeline. The first stage, we sample a scenario. In the second stage, we create a task and environment for that scenario. In the third stage, we run an agent to produce a full trajectory. And in the final stage, we collect the verified trajectories into the data mix. We pair the verified ones with code library task data for covering breadth. This matters because a lot of real requests don't have a clean tool. The right answer is 5 lines of Python. A model trained only on function calling tends to force everything into a tool call. But mixing both styles teaches it when to reach for which. The result competes with much larger general purpose models, but it stays small enough to run next to Farah on your machine locally. And it's open weight, so you can plug it into your own harness too. With that, Hussein, over to you on Farah.
One of our goals in AI Frontiers is to train agentic models to complete computer use tasks. And our bet is that end-to-end synthetic data generation without any human interaction data is going to get us there. Last November, we made our first release with Fara1.5, a small but efficient agentic models that can complete computer use tasks at a level comparable to much larger models. And today, we're so excited to release Fara1.5. This time, a family of computer use agent models across 3 scales, 4B, 9B, and 27B, all based on Qwen 3.5. Fara1.5 is setting state-of-the-art results for model edit size. First, let's see how Farah works on the computer. Farah can handle web tasks that people actually want to complete, like form filling, booking, shopping, and repetitive annoying tasks. So consider a task like applying to the latest intern opening at MSR AI Frontiers. First, Farah starts by capturing a screenshot of the browser. The screenshots goes into the model's context alongside past screenshots, past actions, and the user messages. Given this context, Farah now will predict an action to perform on the browser. In this case, Farah decides to click on the career page. Given this action, we will execute it on the browser, and Farah will get to observe the result of this action and continue in its agentic loop. The action space of Farah consists of native manipulation actions on the computer like clicking on a set of coordinates, pressing keys on a keyboard, and tools for it to manage its own context like memorizing facts so it can act across hundreds of steps. And finally, it also has a tool to ask the user for approval, permission, preferences when needed. On the online mind-to-web benchmark, which consists of 300 tasks covering 100 online URLs, Farah performs at a state-of-the-art level for models at its own size. So compared to its predecessor Fara1.5, Fara1.5 9B almost doubles the performance, going from 35 to almost 65% on this benchmark. But we didn't train Farah just to do well on benchmarks. We trained it to perform well on tasks that people want to use it for. And the key recipe behind this is our scalable synthetic data engine, Farah Gen 2.0. The first ingredient is the environments. We trained Farah on a mix of live web domains across popular websites and complement those with synthetic domains. Synthetic domains mean synthetic websites that we've generated with the help of a coding agent in a tight debugging loop so that we can expose our agent to scenarios that it doesn't see on the live web. For instance, sending an email, booking a flight, and so on that we just couldn't do on the live web. Given the environments and tasks, then we have a solver system consisting of a stronger teacher agent, in this case GPT 5.4, and a user simulator in a tight loop so that they can complete the task. Given the agent's trajectory, now we want to see, did we actually complete the task? And so here comes our last piece, the verifiers. We first judge for correctness. Did the agent perform the task correctly? And we use a set of rubrics that are LLM generated to judge this. The second verifier judges efficiency. How many steps did the agent complete, and did it find the most straightforward path to complete the task? And last but not least is user interaction. Did the agent make up information? Did it do irreversible actions without human approval? Did it not ask for clarifications when it needed to? Given all these ingredients, we can generate a lot of data on the fly, which we can then use to train our model using supervised fine-tuning. So our work with computer use agents doesn't stop with Fara1.5. We have lots of plans to continue building in this line. First, by expanding with always-on capabilities to enable Fara1.5 to monitor the live web, to act in additional environments like Windows and Linux, and use the terminal alongside visual manipulations to complete tasks more efficiently.
Thanks, Veli, Arkarat and Hussain, for the demo. This is incredible work from the team. What if your repository could run itself? Handle issues, automation, and workflows end-to-end without brittle scripts or manual glue? Kelly, an agentic engineer out of MSR Redmond, is here to announce GitHub Agentic Workflows. It brings AI agents directly into GitHub Actions with built-in guardrails and Microsoft-hosted models on Azure. This is a great example of research meeting real developer needs and doing so in a way that's safe, scalable, and practical. Take it away, Pelli.
Hello, everyone. My name is Pelli Doaleu, and I work for Microsoft Research. And today I'm going to talk about GitHub Agentic Workflows. This is a project with GitHub, GitHub Next, and Azure Core, and it aims at using agents to automate all the things. By all the things, we mean automate the entire spectrum of the software development lifecycle, from testing, generating code, documentation, and much more. We think that automation will be the true accelerator of agentic transformation, going from single developer productivity to 100x, 1000x multiplication. But we also think that this multiplication will come with order and orchestration and processes, and not with swarms and chaos. And this is what we plan to build. In GitHub Agentic Workflows, we build agentic human processes powered by GitHub. We have automation through GitHub Actions. We build safety through a sandbox. And we have reasoning through GitHub Copilot CLI. We put the three together, and you have GitHub Agentic Workflows. For example, let's take a look at this process. It's a research plan aside. It is a process that involves multiple agents and multiple human intervention. It starts with deep research on a schedule that tries to solve a problem, like finding duplicate code. It generates a report. The report is inspected by a developer. The developer decides that the findings are pretty good, and it spawns another agent to turn that report into work items. Now, an automated agent, Issue Monster, assigns them to Copilot so that they get turned into code. Issue Monster looks at any issue that's tagged with cookie. It loves to eat cookies. Then Copilot does the usual transformation to code with a dance with the developer, where the developer can add comments and reviews. Eventually, this becomes a pull request and gets merged. This is an example of an agentic human process where multiple agents and multiple humans were involved. Now, agents are dangerous if they are left unattended. Whenever you do an agentic process, you may have adversarial strings entering your process through pull request issues, web queries. Anything coming from an untrusted source may try to take over your agents. We built a sandbox that deals with that. We build a lot of layers of security, and this is one of the aspects that's very important at Microsoft Research. We have the time, the energy, and the people who are able to drill into these problems. This is a very important aspect of agentic workflows, safety. To support the transformation to agents, we also changed the language. We converted the GitHub Action YML, also called file format to, of course, Markdown, which is fairly popular for agents. In our file format, the front matter, the top, is the old actions plus some agentic stuff, and then the second part is a prompt. But of course, you don't edit these files yourself. You use an agent. And you can see on the right that we are using a phone. The future of interacting with agents is going to be natural language based, and you will not need a laptop. It could be a phone. It could be through voice. And this is also something that we're exploring in GitHub Agentic Workflows. Agentic human processes will not only change software development, they will change any process that uses information and uses reasoning. And by that, we mean non-developers, such as people in marketing or sales or operations. Anybody who's doing reasoning and using a Copilot today may want to automate this Copilot. This project is a collaboration between Microsoft Research, GitHub Next, GitHub, and Azure Core. The project is open source, and you can find the link below. Thank you for watching.
Thanks, Feli. It's great to see these tools being available for anyone to use. If you have any questions for him, drop them in the live chat. We've now seen how agents can act, both in open environments and in structured developer systems. As agents take on more responsibility, reliability becomes critical, not just after the fact, but while the agent is working. Joining us as a principal researcher from our MSR India Research Lab, Amit Sharma is here to announce Interwhen. This is a new open source approach to test time verification that lets agents check each step of their own behavior using verifiable properties extracted from natural language. This work sits right at the intersection of theory and practice, and it tackles one of the hardest problems in agentic AI today, knowing when a system is behaving correctly. Over to you, Amit.
Hi, I'm Amit Sharma, a principal researcher at Microsoft Research in India. And today I'm excited to introduce Interwhen, a framework we've built for steering reasoning agents with real-time verification. This is joint work with my colleagues at MSR India, as well as Professor Subbarao Kambampati from Arizona State University. AI systems today are moving from passive generators of text to agentic systems that can execute actions in the real world, either through tool calls or other means. For example, consider an agent that is operating your inbox or executing complex workflows in an organization, or even interacting in the physical world. These agents are equipped with tool calls that can do irreversible changes. For example, it can send an email on your behalf, write to an organizational database, or even move an actual robot next to you. So it is critical not just to verify their final output, but also the intermediate actions. So a central question for us is, how do we go from agentic execution, that's today, to a future with verified agentic execution? Let's look at the current verification systems and their limitations. Typically, the verifier would have access to the model response at time t, the task instruction, and even some domain policies. The first approach uses LLM as a judge, but this is a monolithic verifier, and the LLM might miss nuanced errors, and so this is unreliable. In the second approach, we can use formal verifiers. Now, these are reliable, but they're restricted to math and code. To address these challenges, we have built Interwhen, a real-time framework for agent verification. We'd want to use formal verifiers for general domains, but how do we apply them to this kind of a setting where there might be thousands of tokens and almost everything is ambiguous? The key innovation we have is an LLM-based projection step that automatically breaks down outputs into a list of verifiable properties, the desirable properties you can think of that any solution should satisfy. And now the framework can automatically generate formal spec and create a provable verifier in Python or Lean. Note that the system is not just operating post hoc once the agent is done. It can actually verify a partial model response at any point of time, give actionable feedback, and steer the reasoning model to avoid any violations. We have two important design principles here. First, verification runs asynchronously so that the entire system is efficient. And second, it's plug and play so that practitioners can bring in their existing verifiers as well. Now, let me go tell you how it works in a real-world setting. We are finding that Interwhen leads to state-of-the-art results on agentic benchmarks such as Tau2 Bench, where even small models can rival the accuracy of frontier models. Let's see how this works. First step is to extract verifiable properties. These are structured atomic properties that any solution should satisfy. For example, in Tau2 Bench, we have a scenario with a retail agent, and you'll have a policy which is a lot of text, but then it gets converted to verifiable properties such as a refund must go to the original payment method. And with this property, we can now actually automatically generate Python code that acts as a verifier for it. And this is a one-time operation that can actually be assessed and checked. And then the magic happens at runtime when the variables of the Python verifier are dynamically filled in based on the user's context and the model's current response. For example, here, the agent tries to return some items based on the user's request, but it uses the wrong payment ID. The verifier fires in, it checks that a violation has been made, and gives a message refund to credit card not allowed. We see that in the next turn, the model takes this feedback and corrects its mistake. A key design decision that we have made is efficiency. Verification should not only ensure correct output, but it should also be practical for people to use it. Hence, we have built a separate monitor system that tracks the agent's output in real time and calls verifiers asynchronously for all reversible tool calls. The property here is that the agent's execution is stopped only if an error is found, otherwise it goes as designed. Finally, the framework is general enough, and we have found it leads to significant increases in output quality across tasks, including customer service, as I mentioned, travel booking, logical puzzles, and even ensuring safety of agents' responses. The key benefit that it is plug and play. It works for both proprietary and open weight models and ensures 100% verifier enforcement. That means the agent provides no answer if the verifiers do not pass. I'm excited to announce that we have open sourced Interwhen on GitHub. At Microsoft Research, we believe in open collaboration, and our goal here is to foster a community focused on AI verification and safety, where we can collectively build and test verifiers on real-world use cases and enable a future where all agentic execution is verified. If you'd like to learn more about Interwhen, you can visit the link below. Thank you.
That focus on verification gets us to the fundamentals. It's not just about making models more powerful, it's about making them more trustworthy. Another way to approach that challenge is by rethinking how models are trained in the first place. Let's now zoom in on training. Most language models are still optimized around predicting the next token, even though that doesn't always lead to the best overall response. Let's hear from Carlos in our New England lab about energy-based fine-tuning, a different approach that trains models to optimize meaning across an entire response without relying on complex reward models or external verifiers. It's a clean, principled idea with big implications for how we train and deploy models going forward. Over to you, Carlos.
Hi, this is Carlos. I'm a senior researcher at Microsoft Research New England, and I'll be talking about energy-based fine-tuning. This paper is on training LLMs, so I'll start with an overview on pre-training and post-training of LLMs. In pre-training, the most commonly used approach is next token prediction with cross-entropy loss, whereas in post-training, there are a few phases, starting with next token prediction in the form of mid-training and supervised fine-tuning, or SFT, followed by RL fine-tuning, which is either from human preferences, as in RLHF, or with verifiable rewards, as in RLVR. Let's start by comparing next token prediction with RL, and specifically in a transition example. So the input would be translate to French, the cat is sleeping, and the output is le chat dort. For next token prediction, what we do is evaluate the model for each of the tokens or words in the sentence, and each of those gives a contribution to the loss. Whereas for RL, we generate rollouts from our model, which we rate using a reward model, and we feed that signal back to train the model. Next token prediction and RL both have pros and cons. So for next token prediction, we have stable training, dense signal, and massive parallelizability. Whereas the cons are imitation bias or lack of diversity, distribution shift, meaning that we do not train on self-generated context, only on context from the ground truth. And for RL, the pros would be that there's less distribution shift because we're training on context that are generated by the own model, and there's explicit alignment. Whereas the cons would be sparse signal, less parallelizable because it's doing rollout sampling, and that it requires, crucially, a reward model. What we do is we find the middle ground. We want an algorithm which encourages diverse generations, is robust to distribution shift, has denser signal than RL, is more parallelizable than RL, and does not require a reward. So the idea that we have is let's use feature maps defined on sequences of tokens. And in a nutshell, we made a copy of the model that we want to train. We extract the activation values at different layers as our features. And with those, we define a feature-based moment matching loss, which we optimize by computing rewards. Then we use to train with policy gradients. In this sketch, you can see the ground truth sequence in blue, and in red and green, you can see product generated by our model that we will compare using this feature matching loss to the continuations in the ground truth sequence. Let's look at the feature matching loss that we use. The feature matching loss is meant to measure how well the model's rollout distribution matches the ground truth distribution in an embedding space. So what we do is we sample context from a ground truth distribution, and we compare the conditional distribution of the ground truth with the conditional distribution generated by our model. In practice, computing the expected feature of the ground truth distribution is intractable because we have a single instance for each context. So what we do is optimize the feature matching loss, which we can estimate from ground truth pairs CY. So as you can see, the only difference between the feature matching loss and the conditional feature matching loss is that we replace the conditional expectation with respect to P by just the instance of CY that we have access to. And luckily, the gradients of the feature matching loss and its conditional version are the same, so we're not losing anything by doing that. Next, let's look at a sketch of the whole algorithm. Given a context C, in this case, the kids were excited because, and the ground truth completion Y, it was the last day of school. We feed those we feed the context to a generator, which is the model we want to train. And we obtain a few completions. The summer break was starting, the circus was in town, the weather was nice. We feed the context and all of the completions to a feature network and obtain the corresponding feature vectors, which we then use to construct the feature matching loss and unbiased reward estimates, RJ, that we then use to perform a policy gradient update on the model. Next, let's look at how EBFT compares to the baselines SFT and RLVR in practice. EBFT achieves better cross-entropy loss than SFT and RLVR without directly optimizing for it, even though SFT does optimize explicitly for cross-entropy loss. And EBFT achieves better downstream performance than SFT and comparable to RLVR without access to correctness rewards. In this case, that would be coding correctness, while RLVR does use those kind of rewards to work. And lastly, the feature matching loss that we use in EBFT correlates with the cross-entropy loss, but measures long-range calibration instead of single token calibration like the cross-entropy loss does. These observations hold not only on QA coding, which is the setting I was showing before, but rather also in unstructured coding and in translation. For unstructured coding, we don't have a question and answer structure, but just the coding corpus without structure. And you can see here that we're outperforming SFT and RLVR in cross-entropy and feature matching. And in downstream tasks, we are matching, in some instances, RLVR, and in some instances, we do better. I would like to thank my collaborators on this project, without whom it would not have been possible, as well as the environment at Microsoft Research, which makes it possible to conduct high-risk, high-reward projects that in some cases end up being successful, as has been the case in EBFT, which is already being used to fine-tune models internally at Microsoft. Finally, we're excited to hear your feedback. Feel free to check out the project repo and website on the links. Thank you for listening.
We've looked at how to improve agents, verify their behavior, and train models more effectively. Let's wrap today's episode by taking a step back and looking at the broader AI picture. As agents begin to coordinate tasks, make decisions, and operate across systems, the impact of AI won't just be technical, it'll be economic and social as well. Joining us next is David Rothschild, an economist in our New York City lab. David is going to show us how agent-based systems reshape coordination and markets, and how we can guide this transition towards open innovation-driven ecosystems that benefit society as a whole. This research looks beyond technical performance to the larger question: how do we ensure AI drives meaningful positive impact at scale.
Hi, my name is David Rothschild, and I'm an economist at Microsoft Research in New York City. And I'm here to talk about actually a series of papers that I have been working on with the team out of New York and New England in economics and computation. And we're super excited about this work because rather than focusing on just the short-term impact of AI, we have had the opportunity to look long-term, very broad, about what happens when AI becomes more ubiquitous. What happens when agents become more ubiquitous? How does that affect markets, society? How does it affect all of us? And let's start with the puzzle. AI capabilities feel extraordinary, yet large-scale economic disruption still seems muted. Our explanation is not about model quality or even the harnesses that are increasingly used to capture the processing power, although there's obviously a lot of advancements to come. It's about how AI is being integrated into workflows. First key point, we distinguish three phases of disruption. In this first stage, augmentation, AI speeds up and improves individual tasks, writing, summarizing, coding, inside of workflows built for humans. And in the second stage, automation, routine tasks move under the hood. Humans monitor at a high level, but the underlying architecture, forms, approvals, queues, they remain unchanged. It's still the same human-centered workflow and has the same human-centered then blockage that makes it hard to really hit into the next level of disruption. That's what you get in stage 3, reconstruction. That is where the real disruption happens. Workflows and markets are redesigned from the ground up around AI's native strengths. Parallelism, memory, continuous monitoring, and machine-to-machine interactions. You don't need to build the UX for humans anymore. And the key claim is that most observed gains so far in stage 1 and kind of moving into early stage 2, while the largest welfare gains, the things we're going to remember about this disruption, well, they're in stage 3. And that stage is institutionally hard to get to. So that goes to our second key point. As I just alluded to, the binding constraints to getting to stage 3 adoption are not necessarily technical. Reconstruction of workflows around AI requires delegation of real authority, trust and accountability infrastructure, machine legible data and constraints, and incentives that reward redesign rather than local optimization is getting through that innovator's dilemma and really killing what you have and creating something completely new. So similar to general purpose technologies that come before it, from electricity to computers and the internet, AI disruption has a long adoption arc ahead of it. And that bottleneck is complementary organization and governments, not necessarily raw capability. Third key point, as the AI disruption moves into stage 3, while the leaps in data access and processing power continue to take our attention, it's coordination frictions that become the key policy and design choice. What do we mean here? The lower the communication friction, the lower the lock-in, and the more we unleash widespread coordination of microtasks and payments, the larger are the returns to innovation, and the more equitable the welfare gains are to businesses and consumers rather than the central platforms. Incumbents benefit from constraining agent interaction, while society benefits from reducing it. The structure of future intermediaries, are they going to be open or are they going to be closed? That is what is going to determine whether AI amplifies competition in welfare or concentrates power behind artificial bottlenecks. Similarly, for workers, their surplus also depends on how this delegation, monitoring, and entry are governed. Fourth key point, the scary one. The default trajectory favors entrenchment. Incumbents with existing consumer access are incentivized to maintain control of a market share. And while the organizational and government investments required for open and safe agentic ecosystem, well, they're pretty costly and they're difficult to coordinate. The result may be speed without restructuring, AI that accelerates today's platforms rather than rebuilding them, really sticking us into an endless stage 2. So how do we get to the good place? How do we get to a place in which there is widespread growth and equitable distribution of that welfare. For us, that means building synthetic agentic markets capable of studying and maybe even influencing how different paths to stage 3 can evolve and what do they mean. This is the good thing. For the most part, agents don't know they're in a lab. So there's a lot of external validity to this work. These environments allow consumer assistant agents to interact with business service agents through markets with end-to-end under controlled conditions. And the value of this approach is that it allows us to directly observe things that would otherwise be confounded in the wild. For example, in these synthetic markets, we can examine how market outcomes change when the interaction shifts from human to agent coordination. And what breaks when agents are given real authority rather than just advisory roles. Which government mechanisms, constraints, monitoring, auditability are necessary for humans to provide agency to agents? And this is not always the same threshold, but what is the necessary capabilities for this delegation to work? And of course, you can put that all together, and then you got to look at how red teaming works. What happens when you add malicious actors to the mix? These experiments make reconstruction claims concrete. They show that the ability to add AI just on top of existing workflows is there, but it doesn't produce the same sort of results that you get when you rebuild that interaction layer to really take advantage of what AI has to offer. And so alongside the lab work, we've been developing formal theoretical models as well. And these allow us to study agentic markets at a higher level of abstraction. The role of theory here is not fine predictions. It is about comparative statics. The models allow us to isolate key design choices that are difficult to vary in experiments at scale, such as open or closed ecosystems, centralized versus decentralized discovery with varying feedback mechanisms, different degrees of delegation. They also drive the experimentation that we try, right? So the theory helps drive what we experiment on. And what emerges is consistent. Architectural choices shape equilibrium behavior and surplus allocation. And this is even holding AI capability fixed. So what are the key takeaways? AI disruption is real, but delayed compared to what you may think. Its largest effects will live in this stage 3 reconstruction, not at task level acceleration. And it's not easy to reach the future. Understanding that transition requires a mixed methods. It requires systems thinking and lab experiments and theory all together. And when we do that, what we see is that we need to help not just skating towards the puck, but directing that puck to a place that is going to give higher welfare gains and more equitable welfare gains. Waiting is itself a choice. Early architectural decisions are going to harden quickly, and those are going to have long-term implications for the economy, for society, for all of us. So thank you.
And that's today's Microsoft Research Forum. We covered a lot of ground, from a major new agentic release to tools developers can use today to foundational work on training, verification, and AI's broader impact. This mix is what defines Microsoft Research: curiosity-driven work, collaboration across labs, and a focus on turning early ideas into real-world impact. You can watch all of today's talks on demand and explore related applications, papers, code, and resources on our website. Don't miss out on future releases and the latest work from MSR. Register for Microsoft Research Forum to stay connected. Thank you for joining us, and we'll see you next time.